Okay, thank you. So my name is Shawn Beaulieu, and these are my co-authors. Today I'm going to talk about our work on refractive computation. Before I do that, though, I need to introduce mechanical computation and polycomputation. So when I talk about computation today, I'm talking about the computation of a two-input logic gate like XOR. Here we have inputs A and B and output Q. Every row in this table gives one of the logically possible binary inputs to A and B, and Q gives the output we would expect if the system depicted by this diagram in fact computes XOR. So there's some physical system represented by this figure, and typically that system is some form of electronics like a transistor. Mechanical computing is the effort to realize computation using parts that interact mechanically. That is, instead of passing electrical signals, mechanical computers propagate mechanical forces. So there are a number of ways you might realize a mechanical computer. In our work, we focus on networks of jammed particles having variable stiffness and through which mechanical forces can selectively propagate. The selective propagation of forces is what we'll call computation. And the engineering problem here is how to design the sheet of particles so that you get the right propagation of forces. So I'm going to come back to this system in a minute, but first I want to give a couple of reasons why you'd ever want to do this and why it's relevant to A-Life. So the first is that it's just scientifically interesting. Can you get complex computations in mechanical computers? What are the practical barriers to doing so? Are there any connections to inaction and embodiment? The second has to do with the robustness of computing systems. So let's say there are conditions in which you'd like to compute something, but which are hostile to electronics. If you had a different means of computing using a different source of energy, like heat, for example, you might still be able to realize computation even though you couldn't use electronics. And the third has to do with computational density. So when you look at a computer, some parts play a causal role in computation, other parts are merely aesthetic or passively constrained computation. So for example, the outer shell of your laptop or phone or other things that insulate your device from changing external conditions. If we had a sufficiently advanced understanding of mechanical computing, those parts that constrain computation because of their material properties might still do so, but they could also independently realize computation of their own. So going back to this table, we need some way of representing binary states in our mechanical computer if we want to compute a logic gate. And broadly speaking, we regard non-motion as indicating that a component is off, and motion or a particular pattern of motion as indicating that a component is on. So if we had a network of these components, we could supply inputs in the form of impressed mechanical forces and then observe outputs in the form of changes in mechanical behavior downstream of these forces. So what you're seeing in the top left is a simulation of a two-dimensional sheet of idealized circular particles. And in this sheet, we've got a wall on the top and on the bottom, while on the left and right, we wrap the sheet around so that the left side is touching the right side. Every particle in this sheet is identical except in stiffness, which is given by the degree of shading of the particle, with darker particles being stiffer than lighter particles. To compute a logic gate, we need to specify the inputs and outputs, and the inputs to this sheet are given by the particles having green sticks drawn on their surfaces. The input signals that we supply take the form of external horizontal vibrations at some frequency omega. So we say that an input particle is on if it's being externally driven and off if it's not being externally driven. The output is the particle indicated with a red star, and we read off its behavior by taking the time series of its horizontal displacement and applying a fast Fourier transform at the driving frequency. So if we're vibrating input particles at 12 hertz, then we apply the fast Fourier transform at 12 hertz. So then we use this FFT to calculate a gain value at the output particle. And this is roughly the ratio of the output to the input that tells us if the impressed forces are amplified or muted by the material. So a gain value close to 0 tells us that the material mutes the input forces at the output particle. A gain close to 1 or greater than 1 tells us that the impressed forces are amplified. So then we just go through all of the logically possible ways of stimulating these two input particles and create a unique simulation for each input pattern. We calculate a gain value, and at the end of this process, we'll have 4 gain values for 4 input patterns over 4 simulations. So then we can ask, does the material instantiate a logic gate by taking those observed gain values and comparing them to the Q values that we would expect if the material, in fact, computes this logic gate? So the last component I need to describe is this source particle. And this allows us to evaluate the input case where neither input particle is stimulated, because the source particle vibrates constantly at the driving frequency for all simulations. So this is the approach that was used in a prior paper by our group on the evolution of these logic gates in this kind of sheet of particles, which we call granular metamaterials. And what evolution was allowed to do here was to vary the material properties of the sheet, so the stiffness of the particles and the locations of these ports. I should say that I'm going to show the same sheet of particles in all of my slides, but this sheet is not fixed. So evolution is what determines what the stiffness values are, and it's different than the sheet that you get in this paper that's shown at the bottom. Okay, so everything I've said so far can be compactly represented by this figure. So for a two-input logic gate like NAND, we've got 4 inputs and therefore 4 simulations. And we specify which input patterns are used in which simulation with this vector, where the bold values specify where we expect a high gain at the output particle at this driving frequency if we're computing this logic gate. And the non-bold values are where we expect a low gain. So hopefully that makes sense. So I've said that what we care about is horizontal displacement at the driving frequency. And that's our reference frame for evaluating computation in this system. But clearly other things are happening in the sheet of particles. Hopefully you can see that maybe there's some vertical displacement. Some particles might be moving with a mixture of frequencies or hardly at all. And the reason why we're able to apply our reference frame to this sheet is because of something called the principle of superposition, which says that the full vibrational response of any particle in this sheet is the linear sum of what happens at every frequency. So we use the Fourier transform to isolate what happens at just one frequency. Sorry, skipped ahead too far. And then we discard everything else. But that means that a lot of the mechanical activity here is redundant, and that's mechanical activity that could be used to do other computations. And that's exactly what our group did in another paper demonstrating the existence of so-called polycomputational materials. These are materials that compute multiple things with the same parts at the same time. And this is possible because of superposition and Fourier transform. You can isolate any arbitrary frequency and then ask evolution to optimize for behavior at that frequency. You can also think of this as being equivalent to having 2 specialized observers, one that looks at this sheet of particles and only has eyes for what happens at 12 hertz, and they say this material is computing NAND. And then another observer who only has eyes for what happens at 9 hertz, they look at the same material and they say, no, you're crazy. It doesn't compute NAND, it computes AND. And then we, the external observers, say yes to both of them. It does both things. It's a polycomputational material. I should also say that there's a connection to reservoir computing, given yesterday's talk, the keynote talk. But I think there are important differences between polycomputation and reservoir computing. First is that in our system, at least, we optimize the physical system that's doing computing, whereas in reservoir computing, you typically don't. And then the second thing with multitasking and reservoir computing, you need a separate readout function for each task that you're performing, whereas in polycomputation, you could potentially have a single readout system if that system is polycomputational, so it can do multiple computations. Okay, so there's no reason why we have to stop at just 2 computations over 2 frequencies. We can increase the computational density of this sheet depending on the complexity of the parts that we use or the power of the evolutionary algorithm that we deploy. And that's what we take up in our work. So we ask evolution to accommodate a 3rd and a 4th computation over 2 additional frequencies. And so what this matrix is telling us now is which input particle is stimulated at which frequency in which simulation. And then we ask evolution to do all 4 of these computations with the same parts at the same time. So we fix this matrix during evolution, meaning that every candidate material is stimulated in exactly the way prescribed by this matrix. And then we let evolution run. We use the age fitness Pareto optimization algorithm to minimize the L2 loss between the observed gains at the output particle and the target gains implied by this matrix, where we want high gains where there's bold values and low gains where we want non-bold values, or where there's non-bold values. Okay, so if you look at the best performing material from evolution, which we see drives the L2 loss towards 0, we get pretty much exactly what we asked for, high gains where we want them, low gains where we want them. And we can give a binary representation of this matrix like we have on the right, where we just use some thresholding and then ask if the system computes the 4 logic gates. In all 4 cases, we see yes, it does. Okay, so we've gone from polycomputing 2 logic gates to polycomputing 4 logic gates. But we've actually done a little bit more than that. Some of you may have noticed that there's something weird about this matrix. One thing that's weird is that we don't repeat any of the input patterns for any of these simulations or any of the columns. So taking this last column, for example, which corresponds to the video that you're seeing in the top left, we have input patterns 0, 0, 1, 1, 1, 0, and 0, 1. And those cover the logically possible set of inputs to a two-input logic gate. Now, we've also asked evolution to optimize for behavior that computes NAND and NOR and OR. And because of that, we've got associated target gains with each of these input patterns. So what that means is that if you imagine a new kind of specialized observer, one that doesn't care much for what frequency a particle is stimulated at, or rather can look across frequencies, what they would see when they watch this video is just a collection of inputs and outputs. And this particular collection of inputs and outputs corresponds to the truth table for the imply logic gate. So for this observer, when they watch this video, they'll see a parallel evaluation of the imply logic gate. And so we can do this, or we call this refractive computation. If you look across the operations that were selected for by evolution, that is the operations that compute NAND and NOR and OR, you can pull out additional computations. So we can do this with all four simulations, defining a unique parallel gate for each one. And all of these are universal logic gates. So we give the mean and standard deviation for the best performing materials in evolution in the bottom right. Okay, we can also define computations on the diagonals. I'm going to skip these for time, but you can think of an observer that changes what frequency they attend to, depending on time and context. So this requires a very precise ordering of this input matrix, which means that if you repeat any of the rows, then you're not going to define a parallel gate down any of the columns. That doesn't mean necessarily you're going to corrupt the ability to compute the evolved logic gates. It just means you're not going to get the parallel gates. So what you could do is you could look at all possible permutations of this matrix and see if there are synergies or interferences between these driving frequencies that are used to compute the evolved logic gates. And that's something that we've done internally, but it's not the focus of this work. Instead, we're concerned with those matrices where you do produce these parallel logic gates. And it turns out that for a 4x4 matrix having four possible inputs, there are 512 of these matrices. These are Latin squares. A Latin square is just a matrix where you don't repeat value for any row or column. So because the identity of these parallel gates is sensitive to the precise ordering of this input matrix, if you change the ordering, you get different parallel gates. So what we do is we take the best performing material again, we randomly sample a Latin square, and then we ask it to compute the same four logic gates that it saw during evolution. And that's the constraint that produces these four new logic gates down the columns. So we do the same thing we did before. We ask what are the gain values and is it sufficient or are those sufficient to compute the four logic gates that we evolved for and the new four parallel gates. And we find that the answer is yes under the same thresholding. This works. If you look at the set of 512 Latin squares, you can actually witness the emergence of all remaining 16 logic gates to a two-input gate. And it turns out each one appears in exactly 1/3 of Latin squares, which is a little interesting, I guess. But we can compute the percent success for computing these logic gates for each time it appears in a Latin square. And so here are the results of that. About 80% of the time we succeed in computing these parallel gates. So we can do the same kind of analysis for the evolved gates, which tells us something about the robustness of computation here. So you can think about the computation of NAND during evolution as happening within a fixed environment, right? So we fix the other forces that are used to compute AND, NOR, and OR. So when we sample a new Latin square, we're changing the ordering of these forces. We're effectively changing the environment in which NAND is computed in. And we do corrupt the ability to compute NAND especially, but we do retain the ability to compute the other logic gates relatively well. And it's important to remember that evolution was never asked to do that. So it's nice that we retain some ability to compute under these conditions. So there is more that I have for analysis, but I don't think I have time to get into it. It's in the paper if anybody's curious. So instead, I'm just going to move to the conclusion and thank my colleagues and collaborators. On the left side is the simulation team, and on the right side is the hardware team who's currently working to implement these granular metamaterials in hardware. Thank you.